creating a part which is extrusion. So this means just use a flat plate. We'll put the dimensions here, let's say the same thing as 90 by 30, but 90 millimeters by 30 millimeters in this case. So we have this, it's a bit long, so let me change it to modify that to 15 is better. Okay, so this is the one flat plate I am making, and the thickness is, let's say, 0.5 millimeters. So this is one flat plate that we have created, and what I will do is, instead of creating another flat plate, I will slightly go to properties, create a material properties, elastic, lamina, and E1 is 135 E3, E2 is 8.5 E3, U12 is 0.4, G12 4.283, G13 remains same as it is, as G12, and G23 is around 3.75.
Yes.
E3. So let's say we are only doing elastic here. We are going for composite plies now. Number continuous shell, number of plies, let's say 10. Continue. The regions would be this. Material is the one that we defined. Relative thickness we have 0.1 because we have 10 of those. And rotation angle, I'm keeping everything as same, 0 degrees for that. So that's how my definition for material properties has been assigned for that wall segment. Everybody is following with that process, right? Now what I will do, I will go back to part, and what I'm going to do, I'm going to copy this part and say part 2. Okay, so I don't need to do that. You can create your own part. What I'm trying to do here is I'm simulating a T section. T section means it has a flange and a web, and I'm assuming that both the flange and web have the same geometry. So in case if they are not the same geometry, you can basically create another part from your part module. Okay, so I just created another part. Now what I will be doing, I will rename this part as, let's say, flange. And I will call part 1 as web. Okay, so now in the web, what I will do, I will go to tools and create partition. And partitioning the face, you will soon get to know why we have to create a partition. So I am going to create a partition using sketch method. So it's asking me select the faces to partition. So I am in the web, part is part web. There are 2 parts, but I will be in part web. Sorry, I should be in the part flange, because the web has to get bonded to the flange. So what I am doing, I am going to partition the flange such that they actually get bonded together. So on the part flange, I am going to create a partition. So I select this face. Once the face is selected, it asks me to select an edge or axis. So I will select this. So that way, it has gone in the sketch module. So first I will try to do is to create an axis and dimension it to be at the midpoint, which is 7.5. Then I create the partition face or the partition geometry, and that geometry has to be the same as the thickness of my laminate. So the thickness of my laminate is how much? 0.5. So this is 0.5. Now you see that it has gone there, so I have to make it symmetric. I will use constraints and create symmetry. Symmetry, it will ask me what is axial symmetry. I will say this, and then it will ask me the first entity is this and the second entity is this. Now it is basically placed at the middle. So that way my partition is done. So now if you see, if I press done, you will see that this is a small partition has happened for the face. This is not the same on the other side. The other side has not got partition. It is only this side, this surface is partition. And why I create this partition? Because on this flank and that partition I am going to bond the web, because the web and the flank has to be bonded together. Does it make sense to you guys? So that's creating a geometry definition for flange. Now the advantage of doing the steps I did, if I go to the property, I don't need to reassign the properties for this flange, because I already assigned, I copied it from part 1 after I assigned the properties. So my properties are already assigned for part 1. If I need to change something, let's say I want to change the fly sequence. So let's say I want to say this is 90 degrees. This is 90 degrees as well. This is 90 degrees as well. So that way I change the layup definition for my flange. My web is all 0, my flange has different orientation. It can have different orientation. So that way I can define or I can edit my property. So once that is done, I will go to assembly module, create instance. First I will place any part if you like. Let's say part flange is the first part that comes. Then the next instance that should be there is web, and it should be auto offset from the other instance. So use this checkbox, otherwise they will overlap. So if you use the checkbox here, then you will see both the parts are separated. So you have in this assembly module, you are getting flange and the web. And what we have to do is we have to bond these such that they are like a T-section. So what I will do now is I use this create constraints. So I will create constraint which is face to face. So I will use the face of this web with this flange partition, and gives me the arrow. I will flip the arrow so that they point in the same direction and press OK. Enter 0 value, and you see the orientation has changed now for the web. Now the second constraint I will be using is point to point constraint, coincident point. So I will pick this point and place it on this. So now you see your T section is basically created. Okay, the Z is pointing down, the global axis, if you see, Z is pointing down, X is like in the length direction, Y is in this direction. Make sense? Everybody is getting that part? Now once that is done, the geometry basically has been defined, it has been assembled, properly assembled. But when you do the simulation, Abaqus does not know that they are bonded together or not. So what we have to do is we have to go to the interactions, which we have not yet touched or we have not yet seen. So we have to go to the interaction module and define the boundary constraints. But before doing that, I will go to the step module and reassign, create the steps, just like we were doing for static static stimulation. So I can also go to field output request number 2, let's say for composite. Now you will see that there are 2 composite layers, one for the flange, another for the web. So I will select for layup number 1, I pick stresses and strains, all section points and all flies, okay. I have to create another field output request for another composite layout, which is now for web. Again, select the stresses, select the strains, all section points. Okay, so I have created 2 field output requests. One is for the flange, another one for the web. So once that is done, my step module is defined. Interaction is the module, that's what I wanted to show you, how to define the bonding connections. So here you have to go to this constraint manager and create tie constraints. Tie basically means you are bonding the two surfaces together. They are glued together, they cannot move anywhere else. So what I will use, I will do the tie constraints. It will ask me master surface and slave surface. So I will select master surface. It will ask me the regions of master surface. So what I will do, I will actually select only the part that I need in my view module and select this surface because that's a master. And for the slave type, again surface, I will make an invert display option and then select this surface for the web. So once that is done, you will find that all the flanges and webs have been defined. So I will again bring all of the parts together, and when I say edit, you will see that the bonded connections has been defined at the interface. At the interface of the flange and the web, the Abaqus now considers that surface as properly bonded. Okay? So that's done. Once that is done, now we have to go to load. So I will apply uniformly distributed pressure load at the top. So let's say I select surfaces, I only apply a uniformly distributed pressure load. And the boundary conditions, simply separated boundary conditions. Now the simply separated boundary conditions should be at this edge, which is U30, and also another boundary condition at this edge. So U3 is 0 for that. Okay, so loads and boundary conditions have been defined. Now I have to go for meshing. So for mesh, we have to go to individual parts. Mesh has to be for bottom up, so controls bottom up. Then the seeds, I can define the seeds for this for size. Let's say 2 millimeter is the size. And then I will also use controls for faces of solid regions. Select this solid regions faces and say structure and quad, and then I will mesh it by preview using preview boundary mesh. Create a mesh here, and once this surface is meshed, I will use bottom up mesh technique where I will use extrude. Source sides are this, and the vector for extrusion is from this surface to this surface, and so meshing is done. I am not going to do associate mesh with geometry for all the surfaces because I know which surfaces I am using. So I am using the top surface, and then I will use associate mesh with geometry technique to select all the elements on that side and deselect it, so that way my mesh has been associated. This is for part flange. Similarly, we have to go for part web, but before I go to part web, let me also do the quick change here. Element type has to be continuous shell. So that's done. Now I am ready to go for part web. Again, mesh controls bottom up. Mesh element type is continuum shell. Mesh again controls, now faces of solid regions. Pick any spaces that you need. Put it as a structured mode. Apply seeds. Same size as I have been using there. Now you can create a mesh on one surface. Create a bottom up mesh by selecting the source side, then the vector here, and that's done now. The only two sides I need to associate with I'll be using, which are these sides or these surfaces. So I'll select this, deselect that, that's done. Now similarly at the bottom, I will select this, select that. So everything has been defined, so I'm ready to submit the job. If I'm not missing anything, it should run. Otherwise, there will be some errors, I will find it out. So I will submit it. So it has been submitted, no errors and warnings, many warnings, but no errors, so we are good. The warnings are there for the time constraints that we applied, but the simulation, that's not a significant concern for us. That simulation has been done now. So if I see the results, so you see that our deformed, first thing you have to do is to go to options, common, and select that as one scale because it will not be an accelerated mode of deformation. So this is basically the deformed state for individual plies. Now you will see that the plies are stacked in the manner we need it. So for the web, you have plies vertically, and for the flange, it is horizontal. Okay? Does it make sense to you guys? So result section points, you can go to individual plies and find out for how the stresses are changing. And you see the plies are stacked up for the flange, and for the web it is horizontal. So that completes that simulation exercise for T-beam. I will assume that you will also